Okay. So in our last session we have discussed about center of gravity. Okay, how to find out the coordinates of the center of gravity, and that how it comes from actually weight actually. So you have like m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3 or whatever, that sigma mn divided by sigma mx divided by sigma m. Okay.
Yeah.
So that is the x coordinate. So in 3D you will have three coordinates x,
Yeah.
y and z. So similar formula holds good. Okay.
Yeah.
So the center of gravity is nothing but kind of in a body where you can assume that whole mass is getting concentrated at that point. The effective mass is getting concentrated at that point. Okay.
Yeah.
So it's a very important. It's very important to know the CG. Okay. So we have discussed various geometries where the CG lies, like a rectangular cross section. So we had shown where it is lying, and in a triangle where it is lying, and for a cone where it is lying, that CG. So it is important to know where the CG lies. Okay. And then now we'll discuss about moment of inertia. Okay. So there is a relationship between what it is in the linear motion and in the rotational motion. Okay. So in linear motion, your force is mass into acceleration. Okay. And in rotational motion, the corresponding thing of force is torque. Okay. And corresponding to mass, here it is moment of inertia. Okay. And alpha is your angular acceleration. Okay. So I is called moment of inertia. That means there are two terms here. Inertia. Inertia is the property of any substance which opposes things. Okay, like Newton's first law of motion. Okay, so there we say like inertia of motion or inertia of rest or whatever. So if you are so in linear motion, if you are a heavy body, okay, then if you are in motion, you need more force to bring it to rest.
Yeah.
Or if you are in rest, you need high force to accelerate it or whatever. So force is equal to mass into acceleration. Similarly, in rotational motion, torque is equal to I into alpha. Okay. Then in the previous session on circular motion, we are told that that linear acceleration is dv by dt and angular acceleration is d omega by dt. So corresponding to v there is omega. Okay. And corresponding to a there is alpha. Okay. And similarly corresponding to force there is torque. Okay. So these are linear, and this is rotational or the rotational motion. So then we told that the centripetal in a circular motion, centripetal force is equal to m force is equal to mv square by r. Okay. So or it is mr omega square, right? Okay.
Yeah.
So we told that like this A is equal to r omega square and V is equal to r omega, right? So this is the thing how we get, like say A is equal to dv by dt, we say. Okay. So this because this dv by dt this so you can take it as dv by dt, and this V is again V is again ds by dt, right?
Yeah.
Okay. So d by dt, then s we have told in a circular motion, this your s
Theta.
Okay. So this is your s. Okay. So this is your that arc. Okay. So this is your radius. Okay. So s is equal to r theta, right?
Yeah.
Okay. So this d by dt of r theta, right?
Yeah.
So this becomes d by dt of r theta. So this becomes r omega, r into d theta by dt.
Yeah.
So right.
Yes.
So this acceleration become d by dt, then r d omega by dt. Okay.
Yeah.
So acceleration, so r, okay,
d theta by dt is omega.
d theta by dt is omega, sorry. Okay, so it will be r
Omega.
This is omega, d omega by dt, na?
Okay.
Okay. So d omega by dt is nothing but your alpha, right?
Yeah.
So a is equal to r alpha. Okay. So linear acceleration is equal to r alpha. Okay. Okay, so a is equal to r into alpha. Okay. So that is the angular acceleration. Okay. So the relationship between linear velocity and angular velocity is there is a r in between this. Similarly, the relationship between linear acceleration and angular acceleration, there is a r there.
Okay.
So one additional r you have to multiply.
Yeah.
Okay. So and then r omega square and mv square by r. So these are all related to circular motion. You can take a picture of this. Okay, so the purpose of introducing this is to say that inertia in circular motion is similar to mass in linear motion. Like not inertia, moment of inertia. So there is a term called moment associated with it. Okay.
Yeah.
So what is moment? Suppose you have a door. Okay. Suppose you have a door, and so for moment, so let us say I am applying some force perpendicular to this. Okay, so you have the door hinge here. Okay, so this is your distance, right?
Yeah.
Right. So you are applying a force here. Okay.
Yeah.
So this force, so this moment is equal to r cross f. R cross f.
Yeah.
So so even if your force is less, if the moment arm is high, then also your moment will be high.
Okay.
So
Understood.
suppose when you are opening the door, if you are opening it from the edge, almost from the edge, then you have to apply less force.
Yeah.
But if you are applying some
From the
force
center.
near the hinge, you have to apply more force. So that it's to create rotation. So you are creating a rotation about the hinge, right?
Yeah.
So
you
to
need to
create
apply more force
rotation,
there.
moment is important. Okay. So in circular motion, to create rotation, moment
That
is
is
important.
important.
So
Yeah, understood.
so this moment of inertia. So now you understand what is moment.
Yeah.
Okay. So for example, you have a rod. Okay. So this rod is fixed here. Okay. So you are putting some weight here. Okay.
Yeah.
That means the more is the length of this rod, the more is the moment.
Yeah.
Right. So let us say this is the length and this is the force. So the moment is equal to L cross A or whatever. Right.
Yeah.
So it will try to rotate about this axis. It will rotate like this.
Understood.
So that's the concept of moment of inertia. So why this moment? Moment means similar to torque. Okay.
Understood.
So okay. So now with this we'll derive moment of inertia for various section. So moment of inertia definition is like this. Moment of inertia is defined as the capability of a system to oppose the change produced in rotational motion of the body. So mass is the will oppose the change produced by translational motion. Okay. What is the change? Acceleration or bring something to rest. So that change, if you want to produce in linear motion, that is mass. But in rotational motion, the thing that opposes the change is called moment of inertia. Okay, in rotational motion. Okay, and the formula for moment of inertia is like this. Okay, so let us say this is my origin. So I have some mass, okay, something like this. Okay, let me say my mass here is m1. Okay, my mass here is m2. My mass here is m3. Okay, then let us say my distance is r1, my distance is r2, my distance is r3. Okay, sorry, r3. Okay, so the moment of inertia is a scalar positive quantity. Moment of inertia is not a vector quantity. So moment of inertia of the first mass. So the total moment of inertia of this system is m1 into r1 square. Okay, plus m2 into r2 square plus m3 into r3 square. So this is the moment of inertia. Okay. So otherwise it can be written as m r square I is equal to 1 to n. So if you have
MIRI.
huh?
MIRI.
MIRI, right? MIRI. Okay. I very so this is moment of inertia, or otherwise it can be is also you can say I1 plus I2 plus I3. So if you have so many masses, the complete mass, the effective moment of inertia is this. Okay. Okay. So this is for many particles. For a system of particles, this is moment of inertia. Okay. Okay. So there are some important things in moment of inertia we need to remember. Like so when you have a, like say you have let us say you have a rectangle like this. Okay. So let us say, okay, so okay, so this is your x-axis, this is your origin. So let us say this is x, this is y. Okay. So you have x-axis and you have y-axis. This is just a rectangular area. Okay. So let us say this is the breadth and this is the height. Okay.
Yeah.
So there will be a yeah. So this is x-axis, this is y-axis, and you will have a z-axis like this. Okay.
Yeah, outward.
It will be like, say we can put a cross. Like normally you put it as a arrow. Okay. So how it is, like say, so you have arrow kind of thing. Okay. So how you represent that towards the like perpendicular to the plane.
Inside plane and outside plane.
So
In magnetic
if you
field.
look it inside the plane, like one will be dot.
In magnetic field we use this.
One will be dot and another will be cross. Okay. So here I am putting a cross. One is inside. So if it is a dot, whether it is inside plane or coming out of the plane, it depends on the arrow kind of. So imagining it as a arrow, you can say like normally it is like this. X, Y means it is coming out of the plane.
Dot means it is inside.
That is right hand thumb rule.
Yeah.
So you start with X, like this X, Y, so it is coming out of the plane. So this, if it is a dot, it is coming out of the plane, right? If it is a dot, right?
Yeah, if it is cross, it is
will be going inside the plane. Okay. So this, let us say, this is, so this is a dot. Okay. So it is coming out of the plane, that arrow. Okay. That means, so this is my z-axis. Okay. So as per, so this is called perpendicular axis theorem. So in your moment of inertia there are two theorems. One is called perpendicular axis theorem. Axis theorem. Okay. So as per that, moment of inertia about zz is equal to Ixx plus Iyy. This is called your perpendicular axis theorem.
Okay.
Okay. So about xx there will be one moment of inertia. about y there will be one moment of inertia. Both the things if you add, that will be about z.
Z.
Okay. That means what is the moment of inertia about x means how the material is distributed
Along
about the x-axis. So if you have more and more material away from x-axis, that means it will have more moment of inertia about x-axis.
Yes.
Okay.
The distance is more.
Because distance is more. Okay. So this formula for this Ixx here is not, we are not deriving it. It is bhq by 12. See, just remember moment of inertia formula is either it is mr square.
Yeah.
Okay. So if you remove that g from this, okay, mass is equal to volume into density, right?
Yes.
Volume into density into r square, right? So this volume will have, so if you remove the density part of it, the volume will have unit h cube, like meter cube, right?
Yeah.
And okay, so this thickness term also, so when you come to an area, that thickness term you ignore.
Yeah. Okay.
So this is for mass, you consider the thickness. So there are two things actually. One is called mass moment of inertia. Mass moment of inertia. Okay. Mass moment of inertia, which is equal to mr square, whose unit is kg meter square. Okay.
Yeah.
So what you are doing here is called area moment of inertia.
We are removing
we are removing density and thickness, only area. So this is area moment of inertia. Okay. So this unit of area moment of inertia is just mm4 or meter 4, whatever. So there is no kg coming into picture here.
Yeah.
Okay. So this area moment of inertia about x axis is bhq by 12. Just remember for rectangular section, and for about y axis, Iyy is equal to hbq by 12. hbq by 12.
Okay. B cube. Okay.
hbq. Just that this is
BH
about
cube. This is HB.
about y axis it will be hbq.
Okay. Understood.
So whichever is parallel to y, that will not have the power.
Q.
Okay. So about x means b is parallel to this, that will not have the power.
Yeah, understood. I understood.
So then as per this perpendicular theorem, perpendicular axis theorem, Izz will be bhq by 12 plus hbq by 12. Okay. So this is as per
perpendicular
axis theorem. Okay.
Yeah.
So So you have some standard moment of inertia. So this one I am telling about area moment of inertia, but you have to take a picture of this.
Yeah.
And then in your curriculum, mostly they have like this mass moment of inertia they are explaining. Okay.
Okay.
So just mass moment of inertia will cover. Okay. Okay. So you have solid sphere, hollow sphere, ring, disc. Okay. So see, you can have a, okay, so not, I am not drawing a circle. Let us say you have a ring of radius r. Okay.
Okay.
So imagine this is a circular ring of radius r. Okay. So this is a circular ring of radius r of and mass m. Okay. So this is a circular ring. So ring, you know, it will not have mass inside. It is just a ring. Okay. So the moment of inertia mi of ring of mass m,
radius r.
mass m and radius r is equal to mr square.
Yeah.
Mr square. Okay.
Yes.
This is very, very important. Okay. This is a ring. Okay.
For different systems.
So why it is so? Because your mass is almost at the periphery.
Yeah.
So you know it is very simple formula, m into r square. That's all. M into r square.
Yeah.
Okay. Because how it will be, like say this total m is distributed like m1, m2, m3, something like that. How we derive it? It will be like m1 into r square plus m2 into r square plus m3 into r square, like so many masses. Okay.
Yeah.
Like say mn into rn square, r square. So all r is same. So finally it will become sigma m
Total
into
of the total mass into r.
So this become mr square. So that is ring. Okay. So this ring, in place of ring, if it is become a disc, let us say this is a kind of a disc. Okay. So instead of a ring, let us say this is a disc. So this disc is kind of, so let us say this is my center. Okay. So let us say this has become a disc. Okay. This has become a disc. So in this disc, actually this disc will be something like this. Okay. So it will have mass throughout. So this is called disc, right?
Yeah.
So,
Understood.
So for a disc, the moment of inertia
Is concentrated on the surface area.
So mi of disc of mass m and radius r is equal to half mr square. That you have to remember. Okay. So ring is mr square. So don't confuse that. Don't think that ring has lesser
Ring
mass.
is hollow in the middle.
So ring is nothing is there. Mass disc means so, but both are having mass m.
Yeah.
So don't think that this should have a higher mass. I am telling it as a mass m. So a ring of mass m will have moment of inertia mr square, and a disc of mass m and radius r will be half mr square. Okay. Then there are some other formulas which we have. We just have to remember. Okay. So this is a ring. Suppose you have a solid sphere. Okay. So you have a solid sphere. So just imagine that it's not a circle. It's a sphere.
3D. Yeah.
It is 3D. Okay. So something like this. Okay. So if it is a sphere of radius r, let us say, if it is a sphere, okay. So just you have to remember this. This value is mi is equal to 2 by 5 mr square. That is sphere. Okay. But if it is, this is a solid sphere.
And hollow sphere.
This is solid sphere. Okay. This is solid sphere.
Then hollow sphere.
Then you have hollow sphere. Hollow sphere. Mi is equal to 2 by 3 mr square. Just remember these values. Okay.
Okay. This you have to remember.
You have to remember. We are not deriving it here.
Okay.
So you just remember that.
Disc is mr square. No, disc is mr square by 2. Ring mr square. Like that you have to remember. Okay.
And these moment of inertia, whatever you have got, it is about the diameter. Okay, not about axis perpendicular to them.
Okay.
So whatever I have drawn here, let us say this is a diameter, this is a diameter. So not about axis perpendicular to
It is
them.
a
This is about diameter, this is also about diameter. Okay. So these are these things are about the diameter.
Yes.
Okay. And this sphere value and all, these are also diameter, about its diameter. Okay. So this will have a diameter and this will have a diameter. So about its diameter. Okay. Why I am telling this diameter? Because about this diameter it will be half mr square. Okay, about this diameter. Okay.
Horizontal.
And about this diameter also it will be half mr square.
Yeah.
But if you imagine about a axis which is perpendicular to the diameter, it will be addition of both.
Okay.
It will be half plus half.
Across z axis, so x plus y. Okay.
Yeah, that is a perpendicular axis theorem. Okay.
Understood.
So these are about diameter. About dia. Mi about dia. Similarly, this is also mi about dia. Okay. But if it is about a axis perpendicular to both the diameter, it will have to add it. That is called perpendicular axis theorem. Okay. And these values you have to remember. These are also about diameter.
Yeah.
Okay. And suppose this circular ring, okay. So now you got, this is my circular ring. Let us say this is my circular ring. So about the diameter, this circular ring has a moment of inertia mr square. Okay. So there is another theorem in moment of inertia, that is called parallel axis theorem. Okay. Parallel axis theorem. Okay. Axis theorem. Okay. What does that parallel axis theorem says? So about one diameter it is mr square. But if you want to find the moment of inertia about a tangent, about this, okay. So that will be, let us say this distance is h, which is nothing but your radius, right?
Understood.
Okay, let me put it as h, distance.
That is r.
Okay. So the as per parallel axis theorem, so this is your tangent, say, tangent. Okay. Okay.
Yeah.
So mi about tangent
along parallel axis.
A tangent parallel to the diameter is equal to mr square plus am into h square. Whatever is the distance that you get, you are adding it. Okay. So it will become mr square plus am, then that is also r square.
Yeah.
Right. So.
H and r.
Solid sphere, hollow sphere, and
disc
then
and ring.
Ring, disc, hollow cylinder, solid cylinder. So ring is mr square and disc is half mr square. So ring is half mr square. So this is a disc, right? So
this for what? Parallel axis theorem.
Parallel axis theorem. So a circular disc. Okay. So about the uniform circular disc. Okay. So you can check actually what is the formula. There looks to be a confusion here.
I'll see in inside.
In the book you will see, like, let us say this is my disk, right?
Yeah.
So disk, I have told the moment of inertia is sorry, half mr square, right?
mr square by 2, yeah.
Actually it is mr square by 2 then, right? So mr square by 2,
Okay.
right?
Yeah,
Disk.
you're taking for diameter, for disk.
Okay. So this, if this is the case, half plus mr square will get added. Okay. Half mr square plus mr square, right?
Okay. 3 by 2 mr.
3 by 2 mr square. Okay. So disk is mr square plus yeah, that is your parallel axis theorem. Okay. Okay, so a similar principle holds good here also. Okay, for a ring, like say, let me say for this ring, it will be
There it is mr square plus mr square.
there it will be mr square plus mr square equal to 2 mr square for ring.
For disk 3 by 2.
This is 3 by 2. So basically, the parallel axis theorem says, let us say, this is my rectangle. Okay. So if this is B, this is D. So my this is H shape. Okay. So this is my B, this is my H. Okay. So this is my B, this is my H. So the moment of inertia about this axis. Okay. Let us say this is XX. Right?
Yeah.
So Ixx is equal to Bhq by 12. Right?
Yeah, BHQ.
Bhq by 12. Okay. Then suppose you want to find the moment of inertia about this axis. Okay. Let us say this is let us say this is O or something. Okay.
O dash.
O dash. Okay.
Yeah.
This is XX dash or whatever. So IO is equal to Ixx plus area into this h by 2 whole square. Okay.
Understood.
So this is your this distance is your h by 2.
No, if this was along y-axis, it would have
b by 2 whole square.
It would have it would have been
HBQ by 12.
HBQ.
So let us say this is my y axis. Okay. This is my y, right?
If you're taking along that HBQ.
So I dash will be equal to HBQ by 12. Okay, then if you find about this axis, let us say MM dash or whatever. So I M dash is equal to, let us say, area into B square.
B by 2 whole square.
B by 2 whole square, right? B by 2 whole square plus that will be HBQ by 12.
That moment of inertia, first axis.
Yeah, so that is parallel axis theorem. So if you, normally we find the moment of inertia about CG, but if you want to find about another axis, you just have to add the total area or total mass into the distance from the normal and the from the diameter. Suppose you want to find at the tangent. So what is the distance of the tangent from the diameter? Normally it will be d by 2.
Yeah.
or a radius.
If you're taking center of mass
Huh.
into this.
Or in a rectangular, if you want to find about this axis, it is just ah square.
Yeah.
Area or mass, like mass moment of
Into
inertia,
the
area
distance.
moment of inertia. So ah square or mh square or whatever, the distance.
Understood.
AD square or md square or whatever, the distance we square into the mass or area will get added. That's all. Okay, that is the concept of parallel. So these are the two moment of inertia formulas.
Understood.
Two important theorems in calculating moment
Perpendicular
of
axis
inertia.
theorem, parallel axis.
Perpendicular axis theorem and parallel axis theorem. And yeah, there are
Different systems that I can see.
yeah. So suppose there are you take a picture. Just you now you understand the concept. You can refer the book and remember like
For different
moment of
systems.
inertia for different standard solid or like sphere, hollow sphere, solid sphere, and different areas and all. Okay.
Yeah.
So in case of solid, it will be mass. In case of standard areas, it will be area.
Yeah.
Okay. So because in mass, density and thickness you are just ignoring.
Understood.
Okay, so there are some more standard sections. Okay, so let us say this is the okay, so let us say this is a rod this is a rod of mass m. So this is a rod of mass m, and let us say this length is L. Okay. So the moment of inertia of this is mlq by 3. Okay.
Yeah.
mlq by 3. Okay. And yeah, so this is about this axis. Remember this, I have put it about this axis, that is the moment of inertia.
Yeah.
Okay.
I have to
But,
remember this.
but if you want to find the moment of this rod, moment of inertia about central axis, about this.
Oh, that
Okay,
will be different.
yeah, it will be ml square by 12. Sorry, this is ml square by 3, it's L square.
Okay.
See, if it is area, it will be mm4.
Yeah.
If it is mass moment of inertia, it will be kg meter square. So here mass is m, L square by 3. Whereas
Kg
above
meter
this
square.
axis, it is ml square by 12. Okay. So how you got this from this?
But both unit is kg meter only.
It will be kg. So moment of inertia unit is equal to
Kg meter.
kg meter square, not
Meter square, sorry.
kg meter square, because length square that is na.
Yeah.
So you can now find out, like from here, how you get this. You can find out, because so now you know the let us say
We
this
can
is
use that theorem.
parallel axis theorem. So
Yeah.
this, so you know this is h by 2. Sorry, L by 2, right?
L by 2, yeah.
So L by 2. So your this by parallel axis theorem, ml square by 12 plus m into L by 2 whole square. Okay. So this become ml square by 12 plus
ml square
ml
by 4.
square by 4. Okay. So this become 12. So 4 ml square, right?
Yeah.
4 ml square. So this
So
become ml square by 3.
3.
So this you get by applying parallel axis theorem, because you normally you find about the CG.
Okay.
So this is the CG, so you got. But about any other axis
You
want
have to use the theorem.
you have to apply parallel axis theorem.
Theorem.
Okay, so this is about different. You can refer your book for different standard formula, but these are some of the. So in summary, mass moment of inertia unit is kg meter square. Area moment of inertia, you ignore density and thickness,
And
it will become meter square or mm4 or whatever. And there are two major theorems. One is perpendicular axis theorem.
Where
one
across
is
z
parallel
axis it is
theorem.
x axis plus y axis. This is parallel.
So suppose you have a disk, okay, and I will tell a little more about this parallel axis theorem. So you have a disk, okay. So mass is m and radius is r, okay. So your radius is r. Okay. So for disk we have told for disk the moment of inertia is half mr square.
Yeah.
Right.
Yes.
That is about one diameter. Okay. So about the other diameter, because it is circular thing, it will be the same.
Yeah.
Okay.
Half
So let
mr.
us say this is diameter d dash. Okay. So this is also diameter, say d1 and d1 dash. Okay. So that moment of inertia about an axis perpendicular to this will be, let us say, about an axis which is, let us say, this axis. Okay. So let us say this is x axis. Let us say this is y axis. Okay. So and this is z. Okay. Z dash. Okay. So I z z is equal to I x plus I y. Okay. So it will be moment of inertia about a axis perpendicular to the plane of the disc will be half mr square plus half mr square is equal to mr square. You just have to add it.
Understood.
Okay.
Yeah.
So normally you just remember for a circular cross section,
it will be the same along both the
circular cross section. Just remember it will be pi d4 by 64. If this is the diameter, about the diameter, the moment of inertia will be pi d4 by 64. About one diameter, like say about this diameter pi d4 by 64, about this diameter pi d4 by 64. Then if you want to find out the moment of inertia about a axis perpendicular to this will become pi by 32 d4. About a axis perpendicular. Just remember
addition
of this pi d4 by 64 plus pi d4
this
by
also
64.
by that perpendicular axis.
Perpendicular axis theorem. Just remember that. So instead of d, if you want to write it as
in r square form.
So d4 is nothing but 2r to the power 4, right? So it is nothing but 16, right? 2 to the 8, so 16r
to the power 4.
Okay. So here it will become pi by 4 then, right? Pi by 4 r4.
Yeah.
Right? Pi by 4 r4. So finally plus pi by 4 r4. This will become pi by 2 r4.
Yeah.
That just you remember. Okay.
Yeah.
So this is about the moment of inertia. Okay. So now we have covered center of gravity,
circular
moment of inertia, circular motion, and there is something called a rigid body. Okay. So rigid body is somebody who, when there won't be any deformation. Okay.
Yeah,
if the distance between different point remains
same,
always
even after
remains same,
force applying, then it is a rigid body.
Then it is a rigid body. So normally suppose I have a body. Okay. So if I apply some force, let us say the distance between these was initially it may be something. Okay. But if it is a rigid body, this distance will remain same. But no body is rigid. It is the molecular distance will reduce and all. So rigid body is an ideal concept. Yeah. Okay. So if I apply a force, after some time the distance will be reducing. Okay. By compression it will reducing. If it is tension it will increase. So rigid body. So rigid body is somebody where there is no deformation. And it will be like
the same before and
the Young's modulus, the other things are all infinite.
Yeah.
Okay. So because what happens now? Why it is infinite? Because your Young's modulus,
there is no delta L.
Stress by strain. Stress by strain. Okay.
Strain is del L
so if
by
E is equal to 0, that means capital E is equal to infinite.
Yeah, because that is del L by L, that is
E is nothing but your delta L by L.
There is no change, no
change.
Okay. Understood.
So we have, with these concepts, we will try to solve some numerical in the next session. Okay. Thank you.